Okay, if people will take their seats, we will be convocating again for the afternoon session on the physical and social sciences. So I hope you all got your coffee. You're all restored to go from the depths of the human brain to the outermost limits of the universe. Eric Gawiser is an associate professor in physics and astronomy at Rutgers, the State University of New Jersey. He studies galaxies, stars, and black holes to understand how these objects form and to probe fundamental physics. He currently serves as a principal investigator of the MUSYC collaboration, a survey, I'm sure he'll mention that, and co-chair of the Large Synoptic Survey Telescope Science Collaboration.
Thanks very much, Henry. So I'm an astrophysicist, and it's the childhood dream of every astrophysicist who grew up watching Carl Sagan, that iconic upstate New York astronomer, on TV, to get to say billions and billions of stars in front of an esteemed audience such as this one. So I want to thank the organizers for giving me that opportunity. I could sit down happily now, but I won't. And not only because my love of an audience is proving surprisingly enduring, but also because there are such wonderful developments in the field of astronomy that I want to share with you today. Now, there aren't billions of stars in this image, which comes from the music survey that Henry mentioned, but I did find one in the right position to dot the I in big data, which we could adopt as a logo if you guys want. But let's start at the beginning. Notice that whoever said this did it in yellow jacket colors. The modern understanding looks more like this. There was a Big Bang, and after Big Bang, there's a period of so-called inflation, during which quantum fluctuations got stretched out to macroscopic sizes, the sizes of galaxies. And those gave rise to galaxies by the present day. We observe these fluctuations in the cosmic microwave background radiation. The first stars, and hence galaxies, formed only 400 million years after the Big Bang, and gradually evolved through a series of processes into the galaxies we see in the universe around us today, like our own Milky Way. During this time, the expansion of the universe that had been so rapid was decelerating due to gravity, exactly like you'd expect from physics, until we discovered, surprisingly back in 1998, that in about the last half of the age of the universe, the last several billion years, something happened that caused this expansion to begin to accelerate. We call that something dark energy. And it's often considered the greatest current mystery in all of physics. And you'll see that the quest to understand it motivates much of the big data work in astronomy. So I like this pie chart telling us what the universe is currently made of, because it shows that all the stuff we really understand, stars and the galaxies that they comprise, even other heavy elements, what astronomers call metals, which is anything other than hydrogen and helium to us, even neutrinos that seem a little bit mysterious, but we can actually make in particle accelerators and detect, are a very small sliver of the total matter, and hydrogen and helium that we understand pretty well, plus those comprise only 5% of the energy density of the universe today. Now, academics are famous for thinking that all research should be about their own specialty. I'm not like that. I think that only 95% of humanity's effort should be spent understanding dark matter, which we really don't understand yet, and dark energy. It's important to keep that all in proportion. I also like this pie chart because it's the first time I've ever seen Pac-Man eating a pie chart. And that would make a lot more sense if the second pie chart were that. They flipped dark matter and dark energy by mistake, but it does look delicious. The advances in astronomy that have brought us into the era of big data derive from technology that was invented as basic research at Bell Labs by Willard Boyle and George Smith. They were awarded the 2009 Physics Nobel Prize, actually half of it, for inventing the charge-coupled device, also known as a CCD. Does anybody know how big these are? Anybody, especially in the back there? I'll give you a hint. There's one inside every smartphone camera. This is what lets digital cameras work. And so indeed, these fit between your thumb and forefinger, and as you know from digital cameras, can have up to about 10 megapixels. The great advances in the recent history of astronomy have come from the proliferation of these charge-coupled devices. Here's a nice plot showing that over a 25-year period, ending about a decade ago, there was a 30 times increase in the amount of glass in large telescopes, as we built 8-meter diameter telescopes, but a 3,000 times increase in the number of pixels available in our CCD detectors. And that really has set the stage for the large data sets we're achieving today with gigapixel arrays on the very near horizon. It's the CCDs, the detectors, that have followed Moore's law for us, therefore enabling great increases in data. Thankfully, it's not faster than Moore's law, so if we can solve it now, we can keep handling it. The first great example of this was the Sloan Digital Sky Survey, a coalition of universities funded by the Sloan Foundation and government agencies. They created a detailed multicolor map of the northern sky over 10 years, starting in the year 2000, with a budget of only $100 million. Generated a 50 terabyte raw data set, that's 2 terabytes when processed, leading to a catalog of 100 million stars and galaxies. So at the low, low price of just $1 per object discovered, which is actually quite cheap by the usual standards of astronomy. Now, the data size doesn't look that tremendous, but bear in mind, this has already been done. And at the time they started in 2000, what looks like medium-sized data today was extraordinarily challenging to handle in a computational sense. And the main reason is not just the data volume that's challenging but tractable, but that in astronomy we tend to make very complicated database queries. And so a database of 100 million objects, when you start to correlate between them and make non-local queries, is indeed a challenge. And this is only solved through collaboration with computer scientists and statisticians. So this is a key lesson for our field. Even when the numbers might not seem overwhelming, we're really always testing correlations and then looking to do data mining to find heretofore unknown correlations across a wide range of database records. The greatest contribution of the Sloan Digital Sky Survey may be this map of the galaxy distribution. What we knew before is outlined in purple here, and this is what we learned from it, a three-dimensional universe with a two-dimensional projected slice. I'd call this a pizza slice since we just did a coffee break, and it'd probably make you too hungry, but that's essentially the geometry being shown here. We also refer to this as a cosmic web, voids with these walls and filaments of galaxies surrounding it. And now we're moving on to the time domain, where we study the same area of the sky over and over again because our detectors have gotten such that we can cover a large enough field of view that we can afford to image the entire sky repeatedly. That wasn't true until about now. And I'll talk about a couple of projects that do that: Pan-STARRS, the Dark Energy Camera, and then the Large Synoptic Survey Telescope. So what's out there available to us to study in the time domain? Things that get brighter and dimmer with time, that we would call variable in photometry. These include variable stars that we use to probe distances to our galaxy and nearby galaxies. Exploding stars called supernovae that we can actually use to probe the entire universe. It was so-called Type 1a supernovae that revealed the acceleration of the expansion of the universe back in 1998, leading to another Nobel Prize recently. And quasars, which are incredibly luminous cores of galaxies revealing accretion onto supermassive black holes with 1 million to 1 billion times the mass of our own sun. We can also study things that move, and that's what we would refer to as variable astrometry. The positions on the sky are changing. This can reveal objects in our solar system that don't rotate simply like the background stars throughout our nighttime sky, asteroids and minor planets. This can reveal binary stars, stars moving around each other, or perhaps moving around a massive planet. So it's a way to find new planets around other stars. And it can reveal nearby stars and let us study them in more detail through what we call parallax and proper motion. So we've now reached the audience participation portion of the talk. I would invite each of you, as I try to explain parallax, to reach out your arm and hold up a finger. Please be very cautious which one. And watch it against the background, and first close your left eye, then close your right eye, and do that back and forth. You see it moves significantly in angle versus the background. The Earth's orbit provides that to us. Every 6 months, we see a nearby star at a different location versus the background stars, and we can use that geometry to infer its distance. We can also see if it's moving continuously, and if you want to model, we call that proper motion. If you're really coordinated, you can model proper motion by taking that finger and going diagonally while you keep blinking back and forth, and see how we can determine, basically decompose those two motions. A great example of this that's been done with big data comes from Pan-STARRS, the first of these great time domain surveys over the entire northern sky. Here's a press release hot off the presses from this month, finding a strange, lonely planet without a star. They used this parallax method to determine that this object is 80 light years away from us, and they used its proper motion through space to determine that it's part of a group called Beta Pictoris, that they know the whole group of objects, mostly stars, formed 12 million years ago. Now, the implied dimness of this object and the implied youth of being part of that group tell us that it can't just be a brown dwarf, which would be a so-called failed star without enough mass to ignite nuclear fusion, but rather it looks like a planet of order 6 times the mass of Jupiter, and yet it's not orbiting a star. So this is an exciting discovery. It's also a great example of a big data press release. I zoomed in a little bit, although I'll read it off for the folks in the back, talking about how Pan-STARRS produces the equivalent of 60,000 iPhone photos every night. From now on, that should be the official unit of data, an iPhone photo. From the public's point of view, it might as well be, after all. That they searched for a needle, this planet, in the haystack of 4 terabytes already taken by Pan-STARRS, which is bigger than the sum of the digital version of all the movies ever made, all books ever published, and all the music albums ever released. Not bad writing. This is also a typical astronomy press release in that they've got a picture of this exciting object, and it's this incredibly puny little dim red dot. So to go along with that, as is typical, we have an artist's conception of the planet. See, I told you it was moving versus the background stars. And it's a lot prettier. I like to take a step back and think about the different people involved in this, and I feel like from the artist's point of view, they're going to say, you guys trolled 4 tera-somethings and found a little red dot, and in 30 minutes of Photoshop, I was able to create this gorgeous magenta planet. So I think it all depends on your point of view. But we persevere nonetheless. And indeed, the next step in our transition to big data is the dark energy camera, shown here on the 4-meter telescope at the Cerro Tololo Inter-American Observatory down in Chile. Here's the actual focal plane with so many CCDs now, getting up almost to 1 billion pixels. And this dark energy camera is intermediate between Pan-STARRS that I just showed you results from and the Large Synoptic Survey Telescope, which I'll talk about next. But it offers time for medium-scale individual surveys, like the one led by Rochester's own Eric Mamajek over in the Physics and Astronomy Department, whose group is using this to search for isolated giant planets, more of the type I just described, and brown dwarfs. They'd have order 1 terabyte of data per night. And then the main project that got this camera built and funded by the Department of Energy is that the dark energy survey is using the dark energy camera to study, well, I'll let you complete that sentence on your own. Dark energy. So let's motivate the Large Synoptic Survey Telescope as the final step in this chain using CCDs. LSST will study the time domain science that I described to you. We'll conduct a census of the solar system by looking for objects like this. This is a near-Earth object, an asteroid. It moves in each exposure and considerably between exposures. Mapping the Milky Way using variable stars to find its structure. And using gravitational lensing depicted here, the actual bending of light by massive objects, as shown through the shapes of billions of background galaxies, to constrain the nature of dark energy. LSST will look like this. It's an unusual design to cover a 10 square degree field of view. The detector plane is several times larger than the full moon in angle. We have a site. They've begun construction. And this is the size of the 8-meter primary mirror, which has already now been polished into both the primary and the tertiary. I said an unusual design, and no one will ever again be allowed to sit on it. We also have soccer games, which I put here not just because they're fun, but also to remind me that LSST is an interesting interdisciplinary collaboration of physicists and astronomers. I actually suggested that we use physicists versus astronomers as our soccer teams, but it was deemed that that might be too controversial and rend apart this wonderful collaboration, so we did East versus West. This is a $600 million project scheduled, barring any budget issues in Washington, which of course are unlikely, to start in 2022. The director is Steve Kahn. And quite interesting for this audience, data management is a built-in part of the budget, the survey design, the data reviews from NSF, the conceptual design reviews from the Department of Energy. Data management is intrinsic to the project, so we understand how important it is. That's another lesson learned from the Sloan Digital Sky Survey. So LSST can also be depicted this way. This stuff up here with these horrible units of magnitudes just means that this can see objects 100 million times dimmer than your eye in each exposure. And the main point to make here is this is the telescope. It takes images. Those images will be reduced into catalogs. And the real way to think about the data from LSST is that final database. And this is why we not only call it the Google Index of the Optical Sky, but Google's a partner in the project. The data volumes are going to be extraordinarily challenging for us. Each image is 6 gigabytes. We get one every 17 seconds. Do about 1,000 visits, which is a series of 2 back-to-back images on a location in the sky per night. That'll reveal 15 terabytes of raw scientific image data every night, which lets us redo the Sloan Digital Sky Survey each week over a 10-year period. 60 petabytes of raw data over the 10-year survey. When we all are done, we've got an 8 terapixel image of the sky in 6 colors and 1,000 such frames to make a movie of. Tremendous information on things that go bump in the night, if you will. Final catalogs are expected to have tens of billions of observed objects split about evenly between galaxies and stars, and about 30 trillion individual photometric measurements. And one of the greatest data challenges actually comes from the things that do go bump in the night. We get about 1,000 events per observation, or 1 million events per night over 10 years, and we've promised the world community that we'll process and transmit alerts on everything that's changing in the sky within 60 seconds. Any volunteers to help with that? All right, so one other thing I should point out is this is actually a high fraction of everything we can observe. There are 100 billion stars in the Milky Way and 100 billion galaxies in the observable universe. Coincidence that it's the same number? Probably, because we know that our universe is bigger than our observable universe. One of the great embarrassments of cosmology is we don't know if it's finite or infinite. And that's a conundrum you're welcome to ask me about, but it's probably best pondered over a drink or two. So one other enabling technology for astronomy I should mention that's come along in parallel are high bandwidth radio correlators that enable the existing Atacama Large Millimeter Array, or ALMA, which is in the Atacama Desert of Chile, where some portions have never recorded rain, data cubes of 100 gigabytes, and about a petabyte per decade of raw data, and then the still vaporware square kilometer array, which will come out in a little over a decade if all goes well, at a significant price tag, and will generate petabytes of raw data per night. The square kilometer is not the field of the array, it's the total collecting area. It has baselines of up to 1,000 kilometers. And the advantage of these radio interferometers is that you get the angular resolution as if you had one huge dish 1,000 kilometers around, even by just sparsely sampling that whole idea. But you have to be very cautious how you combine the signals to do that, and that's why this technology and the data volume are so challenging. Now, those of you who speak Espanol will understand why ALMA is my favorite acronym. Alejandro is smiling. It means soul in Spanish. It's quite lovely. Well, I have to say SCA is not too bad either, as these go. So just to mention things you might ask me about later on at the reception, if you're going to make the mistake of asking me about my research and giving me an excuse to talk about it at length, these are projects I'm involved in. They're all in collaboration with Manish Parshar's group at the Rutgers Electrical and Computer Engineering Department. And it turns out the Xerox folks up in the front here also collaborate with Manish. So he's quite active in this field. Some interesting problems ongoing. And the one that we'll have to solve as a full community, by this I mean astronomy, physics, computer science, statistics, is to develop faster algorithms to measure the clustering, essentially correlation functions, of billions of galaxies, because that's a fundamentally n-squared operation until you get clever about it. And that is not a good thing with billions of objects. And so I'll offer my conclusions. Large astronomical surveys have identified raw imagery processing, clustering, and non-local database queries as the biggest computational challenges. The next generation of surveys is coming soon, already here in some cases. It will revolutionize astronomy, which had traditionally been a relatively small-scale science. And big data in astronomy promises huge advances, including the identification by LSST of Earth-killer asteroids, although I should note it cannot protect us from them. That's Bruce Willis's job. Finding more Plutos in our census of the solar system, which should help because Pluto feels rather rejected and lonely at present. Mapping the structure of the Milky Way's billions and billions of stars, and using billions and billions of galaxies to determine the nature of dark matter and dark energy. Now, we like to make these promises. It's possible this won't work at all, especially this last point about dark energy. We might even find out there's no such thing as dark energy, and Einstein just got general relativity wrong. Who knew? But one of the fascinating things in the history of astronomy has been that our surprises have been even more exciting than our promised discoveries. And that's a trend that I can predict with confidence will continue. Thank you very much.
So you mentioned at the end that faster clustering algorithms is a key computational or algorithmic challenge. Off the top of your head, can you think of other algorithmic breakthroughs that have been very important for astronomy within the past decades? Because you mentioned a lot about improvements in the hardware and data collection and curation, but in terms of algorithmics, there's suspense left over drinks.
Well, I'll just give you a quick response on that, and then we can talk some more. So there's an astronomical virtual observatory. There are US and European versions of it that seek to curate these large data sets. And they've done a lot of work on how to handle these database queries, things that improve beyond just SQL. And that's really going to be fundamental. LSST has adopted a lot of those, and it's going to use a SciDB platform for handling the large databases. So that's someplace where we benefit from work that's done outside of the astronomy field in just the study of large database architecture.
Other questions? Okay, well, let's thank our speaker.